Okay. We are, in fact, getting down to the end. Here's our current weighted syllabus, where you're down to the very last few assignments here. So tonight, your height, weight, data analysis homework is due. Tomorrow, your what will I learn is due. About half of you have already filled that in. And then we're down to the exam, which will be Thursday. Basically, the in-class portion will be here. Those of you in the feed section will be in room 384 like last time. So I doubt that will take you 2 hours, but that'll be up to you. I'll go through that. The take-home portion is like last time. There'll be a few questions you have to answer in Excel and turn in by 11 p.m. So again, you've got a window of opportunity on that. So they'll work pretty much just like last time in terms of how the class will proceed. Here's an overview of the exam. Okay. Okay. So the in-class portion has 3 questions for 100 points. There's going to be a question asking you to talk about alpha and beta risk and the effects on alpha and beta risk of standard error and sample size, things of that nature. That's going to be question 1. Question 2 is going to ask you to have a discussion of evaluating data samples using a T versus a Z distribution. If you want to review that, I'll post the slides so you can have it in the course room too. And the third question is going to ask you what you know about confidence intervals and how to interpret them. So those are the 3 questions. Typically, people on these questions write anywhere from a little more than a half page, sometimes a little more than a page essay. So all three are essays. So people plan to write. So if you want to think about those things before you get to the question, it is open books. If you need to refer to the chapters or anything like that, feel free. But ultimately, all 3 are from my list of job interview questions. So these are questions you could get asked in a job interview. So I want to make sure you kind of know them. Take home also has 3 questions, but all 3 require you to build something in Excel. The first will test your knowledge of confidence intervals of the means. So definitely review your confidence interval chapter. The second is a confidence interval based on proportions, both of which were the front and back of the same basic chapter. So be able to do confidence intervals for means and for proportions. And the last question asks you to come up with some expected values and covariance correlation data for a joint probability that the question will give you. So you'll basically get a table of joint probabilities and have to take it through the math. What the question 3 in particular says is you must do the math. Okay, so know how to work it out. It says if you want to use the correlation and covariance function in Excel to check your answer, please do so. So I don't expect anyone to turn in the exam Thursday night with a wrong answer. If you just run the Excel version of the tool, you'll know exactly what the covariance and correlation are. I want to make sure you can derive the calculation going through it. So being able to take that deviation and go through that. So everything you need to do any of these is either in your book or in the lectures we've done for the last few weeks. So back up a little. The homework you're doing right now is on ANOVA and regression. That's really testing your knowledge of those things. So the exam is backing up just a little bit to make sure that the prerequisites to that are in your knowledge base. There's only going to be those 6 questions as we go through. Okay? Questions, comments on that before we get into kind of review? All right. Okay. We're only 5 minutes in. We've already covered the exam. Excellent. Yes?
Did you say that we're given a table like of values where the joint probability was already done?
Yeah, I'm going to give you, the third question will give you a table of probabilities. Okay, so it'll be an X and a Y basically to it with the values filled in. So from that, you'll have to figure out the expected values of X and Y as well as the covariance correlation. So the problem is I think it's a 4x3. It's not a very big matrix compared to some of the ones we've dealt with. So exactly what you need, we actually did here in class several times. So you should be able to do that. And for the most part, if I did it in class, you have the spreadsheets. So a lot of doing the 3 take-home questions is not so much opening up a blank Excel and getting started. It's spend some time when you read the questions. Think about, when did we do this in class? What spreadsheet do I already have into which I can plug in the right values and I'll be done? So if you can do this in 5 minutes because you're really familiar with what we did in class, great. I just want to make sure that when you're on the job, when it comes time to do this kind of confidence interval stuff, which is pretty routine for entry-level engineers, that you won't flinch. This is actually pretty simple stuff. I just want you to demonstrate that you know it. So my expectation is everyone's going to breeze through it. There's nothing in here is meant to trick you up in any way as you go through. So hopefully you'll find them easy. For the most part, when I created my solution set, I copied spreadsheets we'd already used in class, switched the values a little bit, and I was done. So there's no real magic here. I just want to make sure that given a problem, an open book, you can go back and come up with the results you need to come up with. Okay? The question that's already on the table, so we'll start with it, is to look at doing some analysis on the regression results. So I'm not going to open up your homework solution. We'll use a slightly different one. But we must have done, we did this one, right? We did the hair exercise. So like what you're doing, you're taking a lot of data on weight and height and you're coming up with a regression analysis for it. So this isn't your regression, but it's like the one you're doing in your homework. So the challenge is you've got to, so assuming you've gotten this far, I assume, so you have your output of the tool. What do you look at to figure out how to write your bullets in the document? Okay. So again, when I look at this, I always look at those three numbers first. These two numbers have a positive correlation. The correlation is 0.75. Okay. So within reason, if I know someone's height, I know a lot about their weight. It's not a perfect correlation. If it were a perfect correlation, I could tell you what your weight is just by knowing your height. And we all know that would surprise us if we could do that in our society. But the correlation is quite good. It's 0.75. Remember, correlation is a number from -1 to +1, not 0 to 1. You could have a negative correlation. So on a scale of -1 to +1, the correlation between these two numbers is a 0.75, which is fairly high. Okay, so height is a pretty good predictor of what your weight is going to be according to just looking at the data. Remember the multiple R, this correlation number is only looking at the data. The data are correlated very, very well, is what that value tells you. What the subsequent values are telling you, you could really use, for the purposes of this class, you could use either one, but the adjusted R is really the truly valid one. What this tells me is that although the data is correlated at 0.75, this particular regression only explains 0.51 of it, which is not bad. But it tells me there may be other variables out there that if I found them and used them, I could improve my regression formula. Okay? The most I'll ever get out of my regression is a 0.75, because that's all the correlation there really is in the data. Okay? But there's something about the correlation of the data that is not explained just by height. Height is not a perfect predictor of weight. So this adjusted R tells me the value of this regression. So if I ran 3 different regressions using different variables to try to predict weight, I would ultimately use the one that gives me the best adjusted R. Okay? So this is a pretty good correlation, and the regression is pretty good. Okay. Then I come down here and look at these values. Okay. Because the regression tool runs an ANOVA on the data to make sure that it's worth even differentiating this data. Okay. It's rare to run a regression and have it be insignificant because it can't see the differences in the data. Okay. But in essence, that's what it's doing. It's looking at the regression in the data set versus not. And at 98.32% confidence, this ANOVA looks fine. So if the ANOVA came out bad, I'd have to question whether I can really work with this data the way I do. But normally it comes out fine. The data I really want is this coefficient data right here. Okay, that's my real regression. So this regression basically says that a person, in this sample at least, a person's weight is -200 plus 5 times their height. That's what these coefficients are. The question is, are the coefficients reliable? So I use the term reliable broader. Notice I didn't say significant. So are the coefficients good enough to use? That's the standard in reliability. Okay. Ideally, the height needs to be significant. That's the factor I'm looking to use. So in fact, the p-value on the height is 0.01. So it's pretty good significance as I go through. Notice these are the same right here because I've only got one variable. They won't be the same when there's more than one variable. Okay. But yes, the height is a statistically significant variable. The intercept might not be, but I don't care because minus 200 is way off the scale to what I'm looking to use anyway. So in that notion of the line wobbles, okay, I'm not too concerned with how much it's wobbling way over at a height of negative 200 or a weight of negative 200 because we don't have people that weigh that. So this turns out to be the number that I need right here. Okay. Sometimes you'll have an error in the p-value column, that num error, which I admit I can't explain always why it happens. It could happen because there's no data. It could happen because there's too little data. But sometimes it happens. This weekend, I looked around the different Excel discussion boards, seeing if I could find someone to give me a decent answer as to why it happens, and I haven't been able to find anything. So I would just remind you that when you look, if you have an error in the p-value column, that doesn't mean you can't do your analysis. It just means you don't know what the p-value is. Okay? The other way to know if a piece of data is significant or not is to look at the confidence interval, which you do get even when there's a p-value error. If 0 is in the confidence interval, the data is not significant. So whether the p-value is greater than 0.05 or 0 is in the confidence interval, it means the same thing. So while I can't explain the Excel error, I don't know what's happening internal in Excel that's causing that, okay? I can look at the confidence interval. But like I said, I can't explain the error in Excel. Because sometimes you can get the error to move to a different row by rearranging your columns so it does the analysis in a different order. So I know it's not just a function of the data in the column, it's also a function of the order of the columns. So I can't explain it. But I've never seen the confidence interval come out with errors. So you'll always have that. So in this case, the p-value tells me it's not significant. So I don't trust this equation way out at a weight of negative 200. So if I needed to use the equation way out there, I'd have a problem. But I don't need to use it out there, so I'll trust it. The actual height is significant. Okay, so someone's weight is negative 200 plus 5 times their height, according to this model. Okay, now if I can find another combination of variables that I would run, it might be more significant. Another combination of variables might be less significant, and I wouldn't use that model. In your homework, you're adding ABO blood type, blood group, and RH factor to your model. Those are additional variables you're adding to your model. They might make your model better, they might not make your model better. So the last two regressions you're running, one is just with the height, and one is with the height and other variables. So you're in a position when you write your analysis to comment on a comparison of the two. Does ABO blood group, first of all, is it even a significant variable? It might or might not be. And because you're taking a qualitative variable and splitting it into multiple quantitative variables, it's possible some of them will be significant and some of them will not. So always think about the problem before you do it, so you know roughly what you would expect. You know the larger the n, the more likely something is to be significant, right? So imagine blood groups. You may not know a lot about blood groups, but the most common blood type is an O. So if any of the blood group variables are significant, I would predict in advance it's going to be the O blood type. Because I know I'm going to have more data in a selected population with an O blood type than any other. So if the variable is going to be significant, it's the O term that probably will be. If the data is not going to be significant, I would predict it's going to be the B blood type, because B is the rarest of the 4 blood types. That's just my prediction beforehand. It's possible that with this sample of data, none of them are significant, or all of them are. I don't know. Part of the challenge for you as a statistician is don't read so much into it that you invalidate your own analysis. You're analyzing the data as a statistician, not a nutritionist. A nutritionist will look at your results and say, well, that equation is useful or it's not useful. You're building an equation that says, statistically, this equation is the most significant I can come up with. It's up to a nutritionist who knows the domain to decide if that's something we're going to do. In reality, blood type isn't a good predictor of your weight. I think most of us would expect that. So I'm expecting most of you will see that in your results. A nutritionist working with you would probably stop you from doing the last regression I assigned you. Okay, they'd say, look, I'm a nutritionist. I know enough about stats to know blood type doesn't predict weight. Don't even bother to do that analysis. Okay. And again, you'd go back and forth as a statistician saying, well, do you have any variables that would be more predictive? How about cholesterol level? How about average caloric intake? Okay. Because when I do my measures, now this is a small, so this sample is small compared to your sample. But I'm only getting 0.51 out of this regression. So somewhere, hopefully, there's a variable that will be more predictive. Something should explain the 0.75 correlation. I just don't know what it is looking at this regression. That height explains some of the correlation, but not all of it. Okay. When we ran, in this example the other day, we ran it again with hair color. Okay, so we ended up with this analysis. So let's take a look at it. Now again, a priori, if I think about it before I run the analysis, I'm not expecting weight to be predictable from hair color. If it is, I'll be surprised. But if it is, I'll accept it as a statistician. If it turns out blondes really do have more fun and therefore they don't weigh as much, I'll accept that in the statistics. I don't expect it to be true, but if the statistics says it, I'm going to accept it. And I stress that because as new engineers going out and looking at data, trust me, you will be biased on the job. There will be times where you want to say something's not significant because you don't believe it should be, but the data will say it is. Okay, so as an engineer, I have no trouble with you stating your opinion about what it should be. Just be careful you don't say it in such a way that someone thinks it's your statistician hat on when you say it. As a statistician, the data is or isn't significant. That's all you can say. You run the analysis, you report it out. As an engineer, you draw further conclusions from that. So if I found that ABO group was great at helping to come up with someone's weight, I would report that as a statistician. And immediately, as a nutritionist, if someone works in the health field, I say that's ridiculous. There must be some explanation in a sample bias of some sort that resulted in that happening. Now, the sample you're using in your homework is 1,700 lines. It's very unlikely you have a sampling bias in that data. This sample has 10 lines. It could easily have a sampling bias. But that's why you go with as much data as you're able to come up with. So here's a correlation. This data shows a correlation of 0.85. So adding hair color to the data, the correlation of the data went up. That doesn't mean anything, remember. It just says there's a stronger correlation among all this data. The coefficient of covariance and correlation went up. Don't read anything into that. It just did. But the adjusted R went down. And that's a bad thing for our analysis. So although the data is slightly better correlated, this regression explains less of it than just the one by itself. So just based on that value alone of 0.37, I would have a tendency to stick with the earlier analysis and say, let's just use height. Adding hair color to the model made the model worse, not better. Okay, it explains even less of the correlation. But I'll still go through and do the analysis. The data itself appears insignificant. Okay? So I have plenty of data going on in the variation, but the residual variation is very large. Okay, so the ratio of these two variations was 4.61 with a significance at 0.08. So at a 95% confidence, I can't claim that this regression found the relationship between weight and height and hair color. Okay, Okay. It did find a relationship, but I'm saying the relationship it found is not significant. So whether I reject the analysis because of my low adjusted R, or I reject the analysis because this significance is off, either way, I'm not seeing good things about this particular regression. Okay? And that's what you have to be asking yourself as you do your last regression in the homework, is what does this really look like? So I end up with an intercept, my height, my three different variables. I can look at the p-values associated with these. Let's turn those red. This num, I can tell you, is because I only had one redhead. That's not enough data. Okay, so this one I happen to know why I got it. And so therefore it is insignificant by definition. I can't get a significant relationship out of one data point. Okay, so I should have dropped it from the regression if I had seen that in advance. But if you don't always see the data you're running analysis on because it's in a database or something someplace. But knowing that there's only one person was redheaded, I would have dropped that variable no matter what. So this line I'm not too concerned about as I go through. Okay. But in terms of the rest, I've got terrible significance here. Okay. None of these variables are significant. Even the height variable is no longer significant. Okay, and that's one of my big problems here, is at least on my earlier analysis, my height variable was significant. With 98% confidence, I can say that I can predict the weight of a person knowing their height as negative 200 plus 5 times their height. And that's a significant relation. Might not be the best possible prediction, but it is statistically significant. Okay? What I'm looking for by adding hair colors, I'm trying to improve on that, and I haven't been able to do it. Question?
Yes. What's the number or value for the p-value to be significant or not significant?
Well, I ran the analysis at 0.05. Okay. Most of you are running, I assume you're not changing the significance. You're running at 0.05. Say so in your analysis. So I can't see it in the regression. So I actually can here. This heading right here actually tells me what you entered in the tool. Okay, so if you left it as the default at 0.05, it came out here with a 95. So this number here is driven by what you entered in the tool. This first one is it always gives you a 95% confidence interval. That's why back here on this page, I had entered a 0.1. Okay, but I can tell that looking at this value.
If we ran it at 10 alpha, but then in the discussion talked about an alpha of 5, because if it's not significant in an alpha of 5, it's obviously, well
what we've
necessarily actually, but
what we've actually learned is that you don't really need the alpha factor in this analysis. If you're looking at a p-value, you know more than alpha will tell you. So I can say that with 92% confidence, I can say height predicts weight. The question is that good enough for your client? Okay. I can only say with 69% confidence that brown hair has anything to do with weight. Okay. Again, as a biologist, I know it's even worse than that. But statistically, I can't say much. None of these are actually significant. Adding hair color to the model made the model worse. And therefore, under this model, I'm even less confident in my height model. Because this says it's negative 117 plus 4 times the height. Okay, back here it was negative 200 plus 5 times the height. Now algebraically they're not that far off, but this was a more predictive equation. So this equation is not as good as the first one. So far of the two regressions, my best uses just height to predict weight. Adding hair color made the model worse. You'll probably say similar things about adding blood type. Will probably make the model worse. You'll see that in your data. Had we added cholesterol level or caloric intake or family history, there's dozens of other variables that if we had the data and added to the regression, we probably would have gotten a better regression. Better just means more predictive. This model says I can use your height to predict your weight. Another model might say if I know your height and your average caloric intake, I can predict your weight even better. If I know your height and your cholesterol level and your average caloric intake, I can really predict your weight fairly accurately. Okay, so you're just adding on variables, hoping to get a better regression model. As a statistician, you can't come up with what those variables are. You have to work with someone in the field. So a nutritionist, a biologist. As an engineer working on a mechanical problem, you're both the engineer client and the statistician. So with your engineer hat on, you're evaluating variables you can manipulate in your design, and you would add them to your regression. So in an engineering context, you can play both roles. Just be conscious of which role you're in when you make your observations. It is or isn't significant is a statistical statement. It is or isn't important is an engineering conclusion. If the data is not significant, be careful about drawing engineering conclusions. So the first question is always, is the data significant? Then as a statistician, you're done. Then as an engineer, you ask yourself, is it meaningful? Is it useful? Do I want to go that way? But you wouldn't even ask those questions of yourself if the data is not significant. Okay. So the red stuff here is basically the stuff you want to be looking at and talking about as you write your analytical bullets, trying to figure out what is and isn't significant as you go through.
How many bullets do you expect, like, per section?
Some people are writing 2 or 3. Their slightly longer sentences make multiple points. Some people have 6 or 7 because they're literally only citing one little data value. The fewer longer ones are easier for me to read, but whatever way you're comfortable. Okay. Another question.
So, if the p-value is bigger than 0.05, it's not significant?
Not significant, correct. Okay. Yeah, so in this case, this one is significant. You know, the overall is significant. Okay.
So, like in this example, you have weight versus height, but what if you just have my height versus the entire height, and then you return a p-value of like 80.83, and then you say like 17%. There's a 17% chance that they affect each other. Like,
What are you're talking now? You're asking a question about an ANOVA, not a regression, right?
Yeah, I'm asking about.
Yeah, in ANOVA, if you ANOVA, you're comparing for a given variable, a given factor, height or weight in the case of your homework.
Yeah.
So either one. You're comparing 2 samples of data.
Yeah.
Sometimes the sample is the population versus your sample. Sometimes the comparison is the population versus the pre-aggregated data. That's 2 of them. And 2 of them, the population is young people, the sample is old people. Okay, but it's all the same factor. So you got 2 sets of data. The null hypothesis in an ANOVA is always the same. It says the 2 populations are the same.
Yeah.
Okay? That's always the null hypothesis. So the question when you're on the ANOVA is, can you reject the null hypothesis? That's what you're trying to do. So imagine a case where I think the first one has you looking at your height, all the height data versus just your height data. I think it was the first one. So the null hypothesis says the mean of the sample you drew is the same as the mean of the population. Technically, that's what the null hypothesis is. What that means to us, the interpretation of that is that the sample from which you found 50 people isn't statistically significantly different than the general population of Central Florida that everybody's drawing from. Okay, so what do you expect in that first answer?
You can't reject the null.
Yeah, for the most part, unless there's something different about the way you sampled the data. And there are people in class who legitimately will reject the null hypothesis. Okay? But for the most part, most of you, the 50 people you chose are no different than any 50 people any of us could have chosen here in Central Florida. So if you don't reject the null hypothesis, that's not a value statement. It just says you did good sampling. Okay? You want that in a lot of your engineering stuff. If I'm going to do a lean project in a plant and I'm going to train three junior engineers to go out and take measurements of a process. One person's going to work the day shift, one person's going to work the swing shift, another person's going to work the night shift. Okay, I need to know that the way they take their measurements is in fact the same. So I might send them out for a day and have them collect data on their shift and bring it back and run an ANOVA. The null hypothesis is they collected the data the same. I don't want to reject the null hypothesis. If I do, that means someone wasn't doing it right, and I need to better train my people. So I'm constantly running ANOVAs. Don't presume you always want to reject the null hypothesis. Sometimes you're trying to prove that the three processes are the same. Okay, so if they're not, you know where to look. Yes?
Well, what I was wondering is, say you can reject it, and say like your p-value is like 1.38 times 10 to the negative 12. Can you then say we can say that with 99.9999 whatever?
Yeah, you actually can.
Confidence, it is different.
Yeah, 1 minus your p-value is the confidence with which you can say something. Okay, so that's why we don't really need the alpha number once we have the p-value calculated. Because even though we ran it at 0.05, if we have a p that's virtually 0, then we say at virtually complete certainty that the populations are different. So for your sample versus the total, the first two ANOVAs you're running, for the most part, we don't expect you to reject the null hypothesis. If you do, give some thought to why that might be the case. Did I happen to ask a lot of really heavy people? Did I happen to ask a lot of really tall people? Because that would be the explanation. The statistics would say your sample is different than the population as a whole. So when it's different, then we go look typically and say, why might it be different?
So you could even if someone in the class went around and just asked only people they saw that were taller than them, that probably would.
Yeah, it would show up in the analysis. Another way it might show up is if someone didn't really randomly pick people in the population. Okay, they just made up 50 data points. Think, well, I don't have time to ask. I'm just going to make up data points. Okay, the odds of someone making up 50 data points and ending up with the same covariance as the overall population are infinitely small. It's almost impossible to do. It's how you can tell when someone is cheating on a data collection assignment. You test the data against the population. So typically, if you reject the null hypothesis, it means you either cheated on the homework assignment or you, in fact, did the assignment in such a way you ended up with a different population. I'm not hunting for cheaters here, if you're worried. But if you're rejecting the null hypothesis, that means there is an explanation. You may not be able to find it, but there is an explanation for why the data set is different. Okay? So in your case, I would expect no real difference in the first two ANOVAs. Okay? But some of you have had a difference and it's been legitimate. The next two looked at, I think, all the data against the aggregate data, if I recall. Or was that 5 and 6? That was 5. What was the middle one? Oh, yeah, the young old. Okay? So one of them has you looking at a population of people that are slightly older versus a population that's slightly younger. What do you expect in that outcome?
Shouldn't affect the height.
Shouldn't affect the height. So height, you might not expect to reject the null hypothesis. That old versus young, for the most part, with about 800 people in each population, they're more or less the same spread of heights. What about the other? Weight is the other one.
Could affect the weight.
Could affect the weight. So one group might, on average, be heavier than the other, and the ANOVA would tell you that. Doesn't tell you why, it just tells you that they are different. That age could be, and often when we run these ANOVAs, you might find that if you find a variable that's different, age differentiates weight, then maybe we should have added age to our regression to predict someone's weight. See how they interlock? Your homework didn't go this far. But as I work on these regressions to try to improve them, if there was a statistical difference by age in people's weight, and I'm trying to come up with a regression formula that predicts weight, maybe adding age as a variable would be a good idea. So these things go hand in hand. ANOVA allows you to look for variables that make a difference. Regression tries to tell you how that works into the overall model. How much of a difference does it make? Now maybe the ANOVA tells us they're different, but as a regression parameter, it might not have been significant, not a big enough difference to matter. You can't predict that in advance. But that's how all these tools tend to interact. It's ultimately about getting the best regression formula you can get. That if I have these 6 variables about a person, I can accurately predict their weight. Okay. Now, realistically, as a healthcare provider, I know that there is no regression formula that can accurately predict someone's weight. Your weight fluctuates by pounds every day. Okay, so unless your variables captured what things that are causing that, there's just no way to come up with your weight from a set of equations. Morning weight, afternoon weight, average weight, median weight for the week. What weight am I trying to predict? So as you get deeper and deeper into certain projects, you've got to get a lot fancier in some of the math that you're trying to do going in. Really how you use these kinds of models. Because you're coming up with a parameter. So here I can predict your height as negative 200 plus 5 times your height. But height is significant, but it might have been as low as 1.92. So maybe your weight is negative 200 plus 1.92 times your height. Okay, maybe it's negative 200 plus 8 times your height. Okay, so be careful how you use these values. When it really comes down to using the regression formula, we talk about it as negative 200 plus 5 times the height. But each of these coefficients actually falls within a confidence interval. Okay, that at 90% confidence ranges in this case from 1.92 to 8.07. That's a pretty big spread. So if I were using this particular regression to try to predict, say, future obesity in the population, and it's important that I find everybody in the population who's at risk, even if it turns out they're not obese, but I want to focus on all the people who might become obese, then I probably want to use this upper end of the equation. The predicted weight is negative 200 plus 8 times their height. That's going to maximize the prediction of weight and allow me to target everyone who might become obese, even though I might now be targeting people that if I only use the coefficient of 5, might not have met my criteria. Okay, but I don't want to have any false negatives. So I accept some false positives. I accept alpha risk to minimize beta risk. Some cases might be the reverse. I want to target people. The thing I'm going to do introduces some risks, some side effects of some drug I'm going to give, or some health problems related to what I'm going to ask them to do. So I only want to target people I'm pretty confident are going to end up obese. If that's the case, I'll use this 1.92 coefficient, which will underpredict people's weight. But at that coefficient, if it predicts obesity, these people are going to become obese. If they're obese when I underpredict, they're certainly going to be obese if I use the 5. So see how that works? I could end up using any number of variables that come out of this analysis. I don't really know the height coefficient is 5. What I know is that the height coefficient is between 1.92 and 8. Okay, so if I want to really nail it down, I might go with an 80% confidence interval and tighten that up even more. So that notion of when is a confidence interval getting wider or narrower becomes important again, based on how I want to manage my alpha and beta risk. Now, alpha, beta risk, and width of the confidence interval, those are what the exam questions are going to be about. That's why I say the exam backs up a little. It's going to test your knowledge of the things you need to know to properly interpret all this data. So for the homework assignment, I'm not expecting all that interpretation. If you can give it to me, fantastic. But all these things will be variables. So if you think about an equation that starts to stack up lots of different variables, you can see how complicated your engineering challenge can be. Let me find a spreadsheet that did, what lesson did we do? I'm going to go back to this ANOVA problem and look at the regression. Okay, so I'm going back now to week 13. So we had this problem where we did the conjoint design of the functionality. We ran it through the ANOVA and did our 2-key analysis, and eventually came up with this regression. So that's what I want to look at right now. Okay, so here I have a series of code. This equation is much more complicated, remember. Okay, because it's 573 plus 206 times the first factor plus 123 times the second. So it's a very long and complicated equation. Okay, but keep in mind I do have confidence intervals here. Okay. Broaden these just a little bit. Shrink them down. I'm going to take them down just to integers for the sake of discussion. I've thrown away the decimals. Okay, I'll do the same thing here. Okay, so Oh, I can't do that here. I don't have any data. So notice these come out the same. Why are these values absolutely where they're supposed to be?
Because there's zero standard error.
It's zero standard error. I've only got this was a conjoint study. I tricked myself. I thought I was opening up a true regression. I don't have a true regression model for this particular data set. So let me go back to the one we were looking at then. Don't save that. So I'll have to use this one even though we're talking hair color. But we'll pretend it's real. Well, these weren't significant, right? So nothing was. This regression won't do the job. I'll just talk about this one in the abstract then. So what if I had another set of data here? Suppose I had calories, okay, and it was some factor of 1.4 times caloric intake, and this ranged from 0.8 to 1.9. This one's 6 to 2. Okay. So here's just an artificial example here of a factor. You're always going to have a factor with a confidence interval around it. Okay. So I said if in the height example, I might want to over-predict obesity. So I'm trying to avoid false negatives. So I'm trying to avoid beta risk. So I'm going to use the factor of 8. Okay. Or I might use the factor of 2 on my calories. Or I might use both of them at the same time. I might have a case where I want to use the low value on the height and the high value on the calories. That'll be biased toward presuming you're obese with a high caloric intake even if you're short. So I have all these permutations. If I have 5 or 6 variables here, each one has a confidence. So think of it as a set of permutations. I've got an equation, but the equation for each term, I might actually have 3 different values called a 3-point estimate for what the parameter would be. Height can be anywhere from 1.92 to 5 in the middle to 8 above. Caloric intake might be 0.8 to 1.4 in the middle to 2 above. So each variable parameter actually has this shimmer around it of where it might be. That's what you really want to know when you move this model forward into a simulation tool, is how much could it vary. Because what you want to eventually know is height is really important and calories are really important. It turns out when those two are maximized, cholesterol doesn't really matter. But if you throw out height and keep the calories low, high cholesterol is very predictive. You end up out of the simulation tool identifying that it might be not one general model for what causes obesity, but 2 or 3 different models. If you're tall, you're going to be heavier, but with a high caloric intake, you end up obese. And it doesn't matter what your cholesterol is. Regardless of your height, if you have a high cholesterol input, but you have a high calorie input also, you end up as obese. So there's people that are heavy because they're big. There's people that are heavy because they eat a lot. And there are people that are heavy because they eat the wrong stuff. And a regression model could eventually isolate those things to say there's really multiple reasons. So in healthcare, we can't just treat obesity. We have to treat the cause of obesity. And it turns out there's 4 or 5 different causes that require potentially different treatments. Okay, so you could have a bridge that's going to fall down because it's wearing out with rust. You could have a bridge that's going to fall down because there's too many people driving on it. You could have a bridge that falls down because there's too much weather force strain put on it. And one equation might predict the strain on the bridge, but it's not going to predict when the bridge will fall down. Because it turns out it doesn't fall down on the everyday case. It falls down when one or more of its variables are operating at their extreme. So we paint to prevent rust. Okay, we thicken metal to avoid strain. And we control traffic flow to keep load off the bridge. Okay. But based on the average model, because the regression, if you look at the average from the straight coefficient standpoint, you're looking at the average case. The average case might not be that useful to you as an engineer. Because as an engineer, you're interested in reliability, in cost, in manufacturability. You're looking at a lot of different outcome factors that will ultimately be driven by these as inputs. Your engineering regression is really an input to the final models. If I make the product with these parameters, with these tolerances, what do I get out in terms of reliability, satisfaction, profit, manufacturing costs, manufacturing time? Those are the variables we're actually trying to optimize as engineers. Okay, make the company more money, keep the customer safe, make the product as useful as possible. Those are actually our job as an engineer. So we're usually trying to figure out what configuration of the product will drive those things. So think of it as there's a regression of your parameters that leads to an understanding of the behavior of your product. There's a regression of those that determines the profitability of the business. What blend of products will be best? If you're an industrial engineer, you're looking not just at the product, but also its production. What's the optimum lot size for a production factory? What are the optimum inventory levels to control profitability? It's a chain of regressions. The ultimate business output is customer safety and satisfaction, as well as business profitability. You can make a list of the measures your company cares about. As an engineer, you're ultimately responsible for those measures. Okay, but working backward through all these different regressions, it's always a shimmering model. Everything is confidence intervals. I said at the top of the class, one of the key thing you want to come out of this class with is the knowledge that variance matters. Okay, and variance in prediction shows up as confidence intervals. Confidence intervals are a lot of what you need to know coming out of the basic stat class. Everything shimmers. The points are constantly shimmering, the line is constantly shaking, the model is constantly moving. You can never predict anything with absolute certainty. The regressions you come up with are just approximations using variables that Innova told us were at least significantly different, which we drove out of our data collection practices as engineers. So it all fits together. This class is one long story that leads to the profitability of your business, the satisfaction and safety of your customers. That's what all of us are here for, in different disciplines, obviously, but it's all what all of us are ultimately here for, and that's how all this data ties together as we see our way through. All right? I hope I've answered your question. It's a long answer.
Except for the T-stat.
T-stat. This one?
Is that everything else?
The T-stat is your T statistic. So T equals X bar minus...
That's how you calculate, right? That's how you calculate.
That's how you calculate the p-value. So the p-value is the probability under the T curve. So it's simply a T calculation. The tool's doing that for you. But you have just like Z is the difference of the mean to the target divided by sigma, T is the same thing, but it involves knowing the degree of freedom. So if you're comfortable coming up with the Z factor under the curve, T is the same thing, but you have to know the degree of freedom to look up your TATs. This is your T statistic as you go through. Does that make sense? Yeah. So you could look this up if you had the book has a T table in the back. Unfortunately, it doesn't tend to handle degrees of freedom as large as some of the data sets get. This one is fairly small. We had a regression in class. We had 10,000 degrees of freedom that you wouldn't be able to look up. But if you take the T table and look up the 0.5 confidence alpha for degree of freedom of 7 and 1, you'll get some of these numbers. Okay, but there's nothing on the test where you have to be able to look that up. I'm assuming you can look up the T factor in a test. So, to do your T in Excel, just do a T dist. Okay, notice it asks for your X, your number of degrees of freedom, and whether you want a 1 or 2 tail. So you'll get the T factor out of Excel as you go through. If you know your T value, you can do the T inverse of any given T value, say that one, okay, and a degree of freedom. Oops, that didn't work. What did I miss? That one.
Is it too small to show that you need more?
Oh, I need more data than that. I don't know. Again, this unfortunately is not a formula. It's just the number. So I can't reverse engineer that formula for you as you go through. But this is your T stat. Okay, so pay attention to whenever someone says they're using a T statistic, first thing that should enter your mind is the picture we drew several times here in class. Just draw a Z curve. Okay, so we start with a Z curve. And then draw any distribution shorter and wider than that. It's going to be a T distribution. So if this is Z at 0.05 alpha, this would be your 0.05 at some degree of freedom. That's the difference. Okay, so z is equal to the limit of t at alpha to v, where v goes to infinity. Okay. So if you just keep increasing the degree of freedom on a t curve, it keeps getting taller and narrower until finally at infinity it's the z curve. Okay. So every time you think t, think z curve, draw a wider one for t. That's z, and that's t. It's horribly drawn, but it will cause you to think about it correctly. And that's why doing your probabilities with a t curve will give you better answers than a z. Because if I have my x right here, okay, and I use that original z curve versus the t that's under it, that gap is the error I get using my z. If degree of freedom is large enough, I get virtually the same answer. But because we tend to do this in Excel, my recommendation is always use t. Okay, but that is your error in a z calculation. It's the difference under the curve. So your z will overestimate the area under it because it is a taller curve as it goes through. Okay, so z is your limit of t as your degree of freedom goes to infinity. This should be if you find that equation in your text and the graph that goes with it, that's the key point to keep in mind. Particularly since we have a question on the exam about t versus v. So find that equation and the graph that goes with it in the book. And for Thursday, make sure you know where that is. You'll need it. Okay? All right. Let's close up regression. Yes?
How do you know when you're rejecting your null? Because for some reason I just don't understand that.
Where you what or not?
When you reject your null or not,
You reject the null hypothesis if p is at or below your alpha.
Okay.
Okay. So whenever I look, let's open up a couple of ANOVAs here. We go back. When did we do ANOVA? Is that an ANOVA?
Yeah.
Oh, sorry. Just going back to find some ANOVAs. Here's an ANOVA. Okay, so this was an ANOVA of a two-way data set that we did back in chapter 11. Just picking it up. There's the ANOVA. So for this block of data, we were given on a two-factor ANOVA. Okay, we run the ANOVA tool. Okay. Now, how do I know it's a two-factor ANOVA before I run it? Looking at that.
It's a joint probability game.
Yeah, because a lot of you have asked that in the last couple of days. Is do I use a one-factor or a two-factor? To do a two-factor doesn't mean you have two variables. It means you have two variables where you're told the relationship between them. So if you're not given a table of data, you're not going to be able to do a two-factor model because you have to have the interaction of the two in order to get that. So the fact that this is a table tells me I've got two different factors, brand and humidity level. Okay, so I run a two-factor model on that block of data to get that. Okay. So again, so looking at your p-values, okay, they're here. Okay. Both are very, very small. They're extremely small. So the null hypothesis simply says that the two factors, the means on the factors don't interact. Okay. What I'm finding is that the brand is a significant variable. Okay. Whatever these 5 brands are, there are differences. The null hypothesis says the 5 brands are the same. Always try to phrase the null hypothesis. 5 brands are all the same. Okay? So I only reject that if I can prove statistically that at least one of them is different. Not that all 5 are different from each other. That's a much bigger statement.
So
But
then we're trying to calculate
yeah, so this ANOVA on the ABCD comes out as this row right here. Okay? That's looking at the rows. It's 4 degrees of freedom because there's 5 entries. And it ends up calculating the average variance. So it comes up with the ratio of the variance caused by the brands to the noise is huge. That's the F. Okay, there's a critical F for that degree of freedom. So there's our P. So this number is virtually 0. So because it's less than the 0.5 alpha, I claim that there is a difference among the rows. I don't know which row is different. It could be all 5 are completely different from each other. But this is true even if only one is different from the other 4. I only know that the null hypothesis that said they were all the same, I can reject. So don't overinterpret it. It doesn't mean all 5 are different. This means there's at least one that's different than the other 4. If this value were 0.05002, I would not reject it. Now, a good engineer will say, look, at 0.5002, it's so close to where I would have considered it, I'm going to keep looking at it. That's an engineering call, not a statistical call. It's a perfectly reasonable one. More often than not, the value you get is either way above or way under your 0.05, and you don't have to have that discussion. In this case, the p-values are virtually 0. So with complete confidence, I can say that brands make a difference. And with even better confidence, I can say that humidity makes a difference. That's why you have 2 p-values here. One to tell you whether the rows are different, one to tell you whether the columns are different. Okay. Now the columns were defined as a blocking factor. The nature of the experiment was based on a dehumidifier, so of course the amount of humidity makes a difference. So I'm not really concerned whether they are or aren't significant. So I probably wasn't paying attention to this one at all because I expect that. So this is the real result I was after running the ANOVA. Is yes, among these 5 brands, at least one of them is noticeably different. Okay. Once you know that, then the question always becomes which one is different, and that's where you get into the Tukey analysis.
Is a 2-factor ANOVA, would that be the same as running 2 1-factor ANOVAs if you do it on rows and columns?
It's exactly, good question. So the question is, if I ran just an ANOVA of the one variable and the ANOVA on another variable, would I end up with the same results in 2 different analyses? The answer is yes, if the 2 variables do not interact at all.
So if they're independent.
If they're completely independent variables, running 2 1-factor models will tell you that. In this case, I haven't run that, but they're not. Okay, the output, the effectiveness of the brand is in fact highly dependent upon the humidity level it's fighting.
Is that a way to check for independence in the data?
Yeah, you could. There are easier ways to do it. But yeah, you could run that as you went through. So let's try it. Let's see, data analysis. Let's do a single factor ANOVA on just the brand data. Oops. Group by columns, label in the first row, output range. Let's put that one, say, here. I hate Excel sometimes. What did I do wrong? Oh, you're right. Okay, thank you. Label in the first column. I didn't say I was an expert. So let's try that. There we go. So that's the single factor ANOVA of the rows. It's not it's interesting. Rows alone are not significant, which might not be what you expected. But it says if I don't take humidity level into account, I can't spot which of the brands might be different. So the null hypothesis here is that all 5 brands are the same, and in fact I would only be able to reject that hypothesis at 80% confidence, which says that in terms of this experiment, the first ANOVA says the five brands are not the same. The single factor ANOVA says they are, which means the difference is being driven by the difference in the second factor. There's a strong interaction there. Okay, so that's actually not a bad analysis to run. So by itself, the 5 brands are indistinguishable until I actually put them through their paces with different levels of humidity. Again, I can't draw any conclusion about what that difference is yet. It could be that some of the brands perform better at higher humidities. And that's true if you think about the way humidifiers work industrially. There's some humidifiers that are fine at dehumidifying a room that's never higher than 50%. Okay, but those humidifiers would fail if put into a 95% humidity room. They just can't, they don't have the horsepower to do it. Other brands shine best at the high humidity and are very wasteful of energy at low humidity levels because they're only designed to bring it down to about 40%. So a humidifier is going to be designed for different kinds of tolerances, which is why typically humidity level on a test of humidifiers would be a blocking factor. We expect there to be that difference. In this case, it's so significant that with humidity I can tell the difference between the brands, but without humidity I can't. Okay. So again, in this case, looking at it this way, the natural question would be, what are the differences in the brands? And that's where you go with a Tukey analysis. So we set up our Tukey factor, which looks at the minimum difference between the two, and we set up our block. In this case, we found that the block that had the 797, or block A, this was A, 839 was C, 843 was B, 914 was D, and 937 was E. Always be careful interpreting your Tukey, because remember you had to sort these values. So these 5 values are not necessarily A through E like they would have been over here. So you have to look at these values and figure out where they ended up over here to know that. So A was different than all 4. It had the lowest number. D and E were different than A, B, C, but not different than each other, and had the highest values. And C, B, and C were not different from each other, but they were different from the other 3. So this ANOVA simply proves through that number down here that the 5 are not equal. What Tukey tells us is that there's 3 different configurations here. A, that minimizes the response variable, DE, which maximize it, and BC, that leave it in the middle. So what you would do with that would depend on why you were asking. If the point were to minimize the variable, then you're done, pick A. If your point is to maximize the variable, then you're almost done, pick D or E. Okay, and if you try, you could say pick E because it gave you the biggest value, but be careful about that. That's not a statistical statement. 914 and 937 are indistinguishable statistically.
So if you were doing this for an engineering application, would you look at other variables you're trying to control, like energy consumption?
Yeah, I might. But at least this experiment might tell me if I'm trying to maximize the variable, I don't know whether it's going to be D or E, but D or E do maximize statistically a significant way relative to A, B, and C. So I no longer experiment with A, B, and C. Now I'll go experiment just with D and E on using other variables. But don't read too much into these values right here. Okay, that's horrible to read, isn't it? It's a little darker than that. It's a huge mistake to presume that E gives a higher value than D. Because remember, both of these have confidence intervals that probably overlap. In this sample, D gave a lower average than E. But within the confidence interval, if in reality every time I measured in E, the real value was the low end of its interval, and for D, the real value was the high end of its interval, D might have maximized the variable, but it doesn't show up here. So you're not really looking at true determined values. You're looking at the middle of a confidence interval. So it could be that D will actually maximize the variable. There's not enough data here to know the difference. So be very careful about that. I've seen a lot of managers look at that data and say, well, we'll go with E. Okay. That's like saying you'll pick the stock you want to buy is based on whichever one gained the most on the Dow Jones yesterday. Okay, that's probably not the best way to make investments in stock. It's based on one observation in a confidence interval. Okay, so don't do that. But we can reject A, B, and C. They are statistically different values. So that p-value means everything. And the one tip I give you is people make the mistake of not paying attention to the p-value enough. You think you know the answer when you run the experiment. So if the p-value is close enough, you rationalize a very bad decision. You'll get a p-value of 0.499, and you won't reject the null hypothesis because it's so close to the 0.05, where you should. It is significant. Barely, it's true that it's barely significant, but it is significant. 0.051 is not significant. It just isn't. You can say it's almost significant. I'm fine with that. But the reality is it's not significant. Go increase your N by 1 or 2 and you'll probably know the difference. So don't overread your data. As a statistician, interpret your data accurately. As an engineer, take that interpretation and do with it what you need to do. If the best variable you've got for making a prediction is 0.051 on its p, but it's the best data you've got, you run with it. Sometimes it's something that's only a p of 0.2. And you've only had an 80% confidence that it's right. But if that's the best data point you've got, as an engineer, you're going to run with it. Okay, so always in your mind, always after this class, differentiate things you can say as a statistician from things you have to say as an engineer to get your job done. And sometimes you go with sloppy variables. The more you work with social systems, the more likely you are to use sloppy variables compared to narrow mechanical systems where the laws of physics kick in. Okay, but it's all a function of scale. If I'm used to working with social systems, then a simple mechanical thing where I can measure a couple of forces, F equals ma, gives me all the answers I want. But if you're a material scientist, to you, F equals ma is a macro equation at the material level. You're more interested in the thermodynamics of the movement of molecules. You're down at the 1/2 mass times velocity squared on each individual particle. And I'm not a thermodynamicist. I'd get lost down there almost instantly. But you've got levels of systems that you work with, and the trick question is how much rigor and value are you putting into those basic measures? I grew up. My dad always told me the two most important things to know in life are F equals ma. The other one was you can't push a rope. If you know those two things, you can engineer almost any solution as you move forward. Right? It's true. So as long as you know those two things, you can mechanically design virtually anything. If you need more detail than that, go talk to someone who knows a lot more about thermodynamics than I do. But I don't even work at that level. I work at higher levels of what do people in society do. I'm better at predicting how many cars will cross the bridge tonight than I am at calculating how much stress it would take to knock the bridge down. So each of us covers a different layer in all these different kinds of systems as we work through. But at any of these levels, the exact same statistical laws apply. Don't overstate the stats. Don't understate the stats. Make an accurate representation of what the statistics tell you, and then as an engineer, do with that what you need to do with it, and you'll be fine. Okay? Next question. Are we done? We could be done. It's your session. Okay. Okay, well, why don't we wrap? Okay. I'll hang out if you have questions you just want to ask me, but if we're done as a class, let's be done as a class. We won't drag it out just for the sake of it. Why don't we call it a day? If you have more questions you want to ask me, I'll hang around for a little while. We can talk, or you can come up to my office if you need to. You've got the homework assignment due tonight, so hopefully if you've been struggling with that at all, we talked about that enough today that you'll get it done. I think, and if you're on feeds, and hopefully people who are on feeds trying to get this done by 6 will have time to watch today's class also before tonight, but I can't guarantee that.
I just have a quick question about homework with regards to the ANOVA analysis of the weight versus the aggregate.
Uh-huh.
Do we just use the aggregate means?
Yeah, use the aggregate mean as your data. Yep. Okay, fair question. Yeah, comparing to the aggregate, the difference, like I said, your sample data should match the population data, right? So you're expecting that to happen. But what did you expect to happen when you compared the population to the aggregate data?
Shouldn't be any different.
Yeah, it shouldn't be any different. The variance in the aggregate data should be pretty small by comparison. But whether you're talking about the average height of 1,700 people or the average height of 24 groups of 50 people, the question is the average height in the aggregate going to be different than the average height or weight in the population? You don't really expect it to be different. If you were to plot it, okay. If I were to plot, oops. So if I were to plot the weight distribution over the course of our 1,700 people, okay, it's going to be a pretty wide curve, right? With some kind of an X bar around height 70 inches or weight 140 pounds. I don't know what the means were anymore. Okay, but if I plot the aggregate data I would expect something more like this. Right? So because it's an aggregate, the outliers in the original data in each data set tended to average out. Okay, so if the average on an aggregate is fairly high, that means one of you had more tall people than short people in your sample. If the aggregate is low, that means some of you might have had more short people than tall people. But on average, you expect those things to cancel out in your sample. So if each of you on average had 6 to 8 taller people and 6 to 8 shorter people, for the most part, they cancel out. 8 taller, 6 shorter, there's only some canceling, and your X would be a little bit over. The reverse would be a little lower. So within the aggregate, the data is going to move back and forth, but not as much as in the entire population. And that's just it. That's what standard error is all about. That no matter what your underlying population, which is my blue curve, as you take average aggregates from it, you're guaranteed to come up with something that's even more Bell distributed. Okay. That's kind of the whole. I'm sorry. That's kind of the whole point. You get a narrower distribution at the aggregate, but it shouldn't be a different mean. So if you get a different mean, if your ANOVA is if you reject the null hypothesis on those, I'll be very interested to hear your reasoning. Okay, because just knowing the central limit theorem, I don't expect that to happen. But in fact, your original data is more or less normally distributed. Okay, which is why we expect that. So increasing n squeezes the data, and that's what causes this red curve to be narrower. Okay, that's just increasing n. That's the standard error of the mean. The larger your sample size, the more you squeeze your variation. What central limit also gave us, there's no central limit question on the exam, but I'll draw one anyway. Central limit says basically if the original curve had been this, okay, then your aggregate data would still look like this. That's why central limit is so important. Okay, we didn't need central limit on the homework because the original data was normally distributed for the most part. Okay, but still increasing n shrinks that curve. That's the two factors going on. One is the shrinking of the curve because n is increasing. Central limit is saying as you do that, on average, you'll converge around the expected value of the data set. Okay, so your curve, the blue curve could have been this, but you still end up with a mean. Okay, so so if I go back, I'm running out of my scrap paper here. So that is the last class. I'm out of paper. Suppose I had an exponential distribution, okay, with a mu about here. Okay, if I sample data from an exponential distribution, central limit theorem tells me I'm going to get a normal distribution right here. Okay. So I can either be very good at calculating using the exponential curve, okay, or with a lot less work, I could be pretty good at using my z formula to calculate probabilities. But either way, I can calculate the two probabilities. If n is too small, central limit doesn't kick in, and I better not use the z formulas to make predictions. But if I've run 1,000 cases through an experiment, I can use my z formula on the red curve just as easily as I use the exponential distribution on the blue. Again, because we're in Excel nowadays, neither is really easier than the other. But think back just a few years where you didn't have Excel spreadsheets to do this. And given an option to convert a problem into a z calculation rather than an exponential distribution, you'd have grabbed the z calculation. Again, today you can do it either way, and it's not a problem. Okay, but that's really what's going on. So larger n, okay, confidence interval of the mean says you'll get a narrower curve as you take larger samples. Central limit says that curve will become normal even if the underlying data isn't. So it's the two go hand in hand. Some people lump them both, say both of those things under the definition of central limit. But you don't need central limit theorem to guarantee that distribution will be narrower as n goes up. That's standard error of the mean. Right? When you get your first job, I guarantee your boss will not know that distinction. So you can laugh at them when they say it in a meeting. I heard you were going to say that. Okay? All right? So test on Thursday. You know the 6 questions. I'll be in my discussion threads the rest of the week. If you've got questions in advance, just keep asking them. I'll try to answer them. Otherwise, I'll see you here Thursday for the exam. Uh-huh.
I have a quick question.
Sure.